Semi-automatic ground environment. Background. Earlier systems. Just prior to World War II, Royal Air Force RAF tests with the new chain-home CH radars had demonstrated that relaying information to the fighter aircraft directly from the radar sites was not feasible. The radars determined the map coordinates of the enemy, but could generally not see the fighters at the same time. This meant the fighters had to be able to determine where to fly to perform an interception, but were often unaware of their own exact location and unable to calculate an interception while also flying their aircraft. The solution was to send all of the radar information to a central control station where operators collated the reports into single tracks and then reported these tracks to the air bases or sectors. The sectors used additional systems to track their own aircraft, plotting both on a single large map. Operators viewing the map could then see what direction their fighters would have to fly to approach their targets and relay that simply by telling them to fly along a certain heading or vector. This dowding system was the first ground-controlled interception GCI system of large scale, covering the entirety of the UK. It proved enormously successful during the Battle of Britain and is credited as being a key part of the RAF's success. The system was slow, often providing information that was up to 5 minutes out of date. Against propeller-driven bombers flying at perhaps 225 miles per hour 362 km/h, this was not a serious concern, but it was clear the system would be of little use against jet-powered bombers flying at perhaps 600 miles per hour 970 km/h. The system was extremely expensive in manpower terms, requiring hundreds of telephone operators, plotters, and trackers in addition to the radar operators. This was a serious drain on manpower, making it difficult to expand the network. The idea of using a computer to handle the task of taking reports and developing tracks had been explored beginning late in the war. By 1944, analog computers had been installed at the CH stations to automatically convert radar readings into map locations, eliminating 2 people. Meanwhile, the Royal Navy began experimenting with the Comprehensive Display System CDS, another analog computer that took X and Y locations from a map and automatically generated tracks from repeated inputs. Similar systems began development with the Royal Canadian Navy, DATR, and the U.S. Navy, the Naval Tactical Data System. A similar system was also specified for the Nike CIM project, specifically referring to a U.S. version of CDS, coordinating the defense over a battle area so that multiple batteries did not fire on a single target. All of these systems were relatively small in geographic scale, generally tracking within a city-sized area. Valley Committee. When the Soviet Union tested its first atomic bomb in August 1949, the topic of air defense of the U.S. became important for the first time. A study group, the Air Defense Systems Engineering Committee, was set up under the direction of Dr. George Valley to consider the problem, and is known to history as the Valley Committee. Their December report noted a key problem in air defense using ground-based radars. A bomber approaching a radar station would detect the signals from the radar long before the reflection off the bomber was strong enough to be detected by the station. The committee suggested that when this occurred, the bomber would descend to low altitude, thereby greatly limiting the radar horizon, allowing the bomber to fly past the station undetected. Although flying at low altitude greatly increased fuel consumption, the team calculated that the bomber would only need to do this for about 10% of its flight, making the fuel penalty acceptable. The only solution to this problem was to build a huge number of stations with overlapping coverage. At that point, the problem became one of managing the information. Manual plotting was ruled out as too slow, and a computerized solution was the only possibility. To handle this task, the computer would need to be fed information directly, eliminating any manual translation by phone operators, and it would have to be able to analyze that information and automatically develop tracks. A system tasked with defending cities against the predicted future Soviet bomber fleet would have to be dramatically more powerful, that the models used in the NTDS or data. The committee then had to consider whether or not such a computer was possible. Valley was introduced to Jerome Wiesner, Associate Director of the Research Laboratory of Electronics at MIT. Wiesner noted that the servomechanisms laboratory had already begun development of a machine that might be fast enough. This was the Whirlwind I, originally developed for the Office of Naval Research as a general-purpose flight simulator that could simulate any current or future aircraft by changing its software. Wiesner introduced Valley to Whirlwind's project lead, J. Forrester, who convinced him that Whirlwind was sufficiently capable. In September 1950, an early microwave early warning radar system at Hanscom Field was connected to Whirlwind using a custom interface developed by Forrester's team. An aircraft was flown past the site, and the system digitized the radar information and successfully sent it to Whirlwind. With this demonstration, the technical concept was proven. Forrester was invited to join the committee. Project Charles. With this successful demonstration, Louis Reidner, chief scientist of the Air Force, wrote a memo stating it is now apparent that the experimental work necessary to develop, test, and evaluate the system's proposals made by IDSEC will require a substantial amount of laboratory and field effort. Reidner approached MIT President James Killian with the aim of beginning a development lab similar to the war-era radiation laboratory that made enormous progress in radar technology. Killian was initially uninterested, desiring to return the school to its peacetime civilian charter. Reidner eventually convinced Killian the idea was sound by describing the way the lab would lead to the development of a local electronics industry based on the needs of the lab and the students who would leave the lab to start their own comp. Killian agreed to at least consider the issue and began Project Charles to consider the size and scope of such a lab. Project Charles was placed under the direction of Francis Wheeler Loomis and included 28 scientists, about half of whom were already associated with MIT. Their study ran from February to August 1951, and in their final report they stated that we endorse the concept of a centralized system as proposed by the Air Defense Systems Engineering Committee, and we agree that the central coordinating apparatus of this system should be a high-speed electronic digital computer. The report went on to describe a new lab that would be used for generic technology development for the Air Force, Army, and Navy, and would be known as Project Lincoln. Project Lincoln. Loomis took over direction of Project Lincoln and began planning by following the lead of the earlier RAD lab. By September 1951, only months after the Charles report, Project Lincoln had more than 300 employees. By the end of the summer of 1952, this had risen to 1,300, and after another year, 1,800. The only building suitable for classified work at that point was Building 22, suitable for a few hundred people at most, although some relief was found by moving the non-classified portions of the project, but this was clearly insufficient space. After considering a variety of suitable locations, a site at Lawrence G. Hanscom Field was selected, with the groundbreaking taking place in 1951. The terms of the National Security Act were formulated during 1947, leading to the creation of the U.S. Air Force out of the former U.S. Army Air Force. During April of the same year, U.S. Air Force staff were identifying specifically the requirement for the creation of automatic equipment for radar detection which would relay information to an air defense control system, a system which would function without the inclusion of persons for its operation. The December 1949 Air Defense Systems Engineering Committee led by Dr. George Valley had recommended computerized networking for radar stations guarding the northern air approaches to the United States, e.g. in Canada. After a January 1950 meeting, Valley and J. Forrester proposed using the Whirlwind I completed 1951 for air defense. On August 18, 1950, when the 1954 interceptor requirements were issued, USAF noted that manual techniques of aircraft warning and control would impose intolerable delays, 484 Air Material Command AMC published Electronic Air Defense Environment for 1954 in December. During February-August 1951, at the New Lincoln Laboratory, the USAF conducted Project Claude, which concluded an improved air defense system was needed. In a test for the U.S. military at Bedford on 20 April 1951, data produced by a radar was transmitted through telephone lines to a computer for the first time, showing the detection of a mock enemy aircraft. This first test was directed by C. Robert Weiser. The Summer Study Group of scientists in 1952 recommended computerized air direction centers. 128 The USAF had decided by April 10, 1953, to cancel the competing ADDIes based on CDS, and the University of Michigan's Aeronautical Research Center withdrew in the spring. A 289 Air Research and Development Command ART planned to finalize a production contract for the Lincoln Transition System. A 201 Similarly, the July 22, 1953 report by the Bull Committee NSC 159 identified completing the Mid-Canada Line radars as the top priority, and on a second priority basis, the Lincoln Automated System. The decision to control Bomarc with the automated system was also in 1953. The total consisted of 47 gap filler stations, 75 permanent system radars, 39 semi-mobile radars, 19 pine tree stations, 1 Lashup era radar and a single Texas tower. 223 On 31 December 1958, USAF ADC had 187 operational development. J. Forrester was instrumental in directing the development of the key concept of an interception system during his work at Servo-Chanism's laboratory of MIT. The concept of the system, according to the Lincoln Laboratory site, was to develop a digital computer that could receive vast quantities of data from multiple radars and perform real-time processing to produce targeting information for intercepting aircraft and missiles. The IN/FSQ-7 was developed by the Lincoln Laboratory's Digital Computer Laboratory in Division 6, working closely with IBM as the manufacturer. Each FSQ-7 actually consisted of 2 nearly identical computers operating in duplex for redundancy. The design used an improved version of the Whirlwind I magnetic core memory and was an extension of the Whirlwind Roman II computer program, renamed IN/FSQ-7 in 1953 to comply with Air Force nomenclature. It has been suggested the FSQ-7 was based on the IBM 701, but while the 701 was investigated by MIT engineers, its design was ultimately rejected due to high error rates and generally being inadequate to the task. IBM contributions were essential to the success of the FSQ-7, but IBM benefited immensely from its association with the SAGE project, most evidently during development of the IBM 704. On October 28, 1953, the Air Force Council recommended 1955 funding for ADC to convert to the Lincoln Automated System. 193 redesignated the SAGE system in 1954. A 201 The experimental SAGE subsector, located in Lexington, Mass., was completed in 1955. In 1955, Air Force personnel began IBM training at the Kingston, New York, prototype facility, and the 4,620th Air Defense Wing experimental SAGE was established at Lincoln Laboratory. On May 3, 1956, General Partridge presented NORAD's operational concept for control of air defense weapons to the Armed Forces Policy Council, and a June 1956 symposium presentation identified advanced programming methods of SAGE code. For SAGE consulting, Western Electric and Bell Telephone Laboratories formed the Air Defense Engineering Service ADES, which was contracted in January 1954. IBM delivered the FSQ-7 computer's prototype in June 1956, and Kingston's XD-2, with Joule computers, guided a Cape Canaveral Bomarc to a successful aircraft intercept on August 7, 1958. 197 initially contracted to RCA-FSQ-7, the $2 billion WW2 Manhattan Project. General Operational Requirements GOR 79 and 97 were the basic USAF documents guiding development and improvement of the semi-automatic ground environment. 97 prior to fielding the IN/FSQ-7 centrals, the USAF initially deployed pre-SAGE semi-automatic intercept systems and /GP-37 on April 22, 1958. NORAD approved NIC-ODs to be collocated with the USAF manual ADS at Duncanville Air Force Station TX, Olathe Air Force Station KS, Belleville Air Force Station IL, and Osceola Air Force Station KS. Deployment. SAGE sites. The SAGE system included a direction center DC assigned to air defense sectors as they were defined at the time. Some of the originally planned 32 DC were never completed, and DC were planned at installations for additional sectors: Calypso/Raleigh in C, England/Shreveport LAV Fort Knox KY, Kirtland/Albuquerque NM, Robbins/Miami, Scott/St. Louis, Webb/San Antonio TX. Description. The environment allowed radar station personnel to monitor the radar data and systems status, e.g. Arctic tower radome pressure, and to use the range height equipment to process height requests from direction center DC personnel. DC received the long-range radar input from the sector's radar stations, and DC personnel monitored the radar tracks and IFF data provided by the stations, requested height finder radar data on targets, and monitored the computer's evaluation of which fighter aircraft or Bomarc missile site could reach the threat first. The DC NORAD sector commander's operational staff could designate fighter intercept of a target, or, using the senior director's keyed console in the weapons direction room, launch a Bomarc intercept with automatic Q-7 guidance of the surface-to-air missile to a final homing dive. Equipped fighters eventually were automatically guided to intercepts. The NORAD Sector Direction Center NSDC also had Air Defense Artillery Director ADAD consoles and an Army ADA battle staff officer. And the NSDC automatically communicated cross-tilling of SAGE reference track data to / from adjacent sectors DC and to 10 Nike Missile Master ODs. Forward tilling automatically communicated data from multiple DC to a 3-story combat center CC, usually at one of the sector's DCCF. Planned Hamilton AFB CC-5 near the Beale AFB DC-18 for coordinating the air battle in the NORAD region multiple sectors, and which forwarded data to the NORAD Command Center and NORAD's integration of air warning data at the ADOC along with space surveillance, intelligence, and other data allowed attack assessment of an air defense emergency for alerting the ASAC Command Center's 465 LSAX nodes at Offutt AFB and the Notch, the Pentagon/Raven Rock NMIC/ANC, and the public via NORAD radios. SAGE Communication Systems is the Burroughs 416L SAGE component ESD Project 416L semi-automatic ground environment system was the Cold War network connecting IBM-supplied computer system at the various DC and that created the display and control environment for operation of the SEPRA. Burroughs Corporation was a prime contractor for SAGE network interface equipment, which included 134 Burroughs and /FST-, 2 coordinate data transmitting set CDTS at Radarist. The IBM supplied in /FSQ-, 7 at 23 direction centers, and the in/FSQ-, 8 combat control. The 2 computers of each in /FSQ-, 7 together weighing 275 short tons, force 2450 K, and used about 1/3 of the DC second floor space and at $50 per. The in/FSQ-, 7 at Luke AFB had additional memory 32 K total and was used as a computer center for all other DC. Project 416L was the USAF predecessor of NORAD SAC and other military organizations' Big L computer systems, e.g. 438L Air Force Intelligence Data Handling System and 496L Space Detection and Tracking System. Network communications. The SAGE network of computers connected by a digital radar relay SAGE data system used at NT voice lines, microwave towers, switching centers, e.g. SAGE NNX 764 was at Delta, Utah, and 759 at Mounds, Oklahoma, etc. And at NT's main underground station was in Kansas Fairview, with other bunkers in Connecticut, Cheshire, California, Santa Rosa, Iowa, Boone, and Maryland, Hearthstone Mountain. CDTS modems at automated radar stations transmitted range and azimuth, and the Air Movements Identification Service AMIS provided air traffic data to the SAGE system. Radar tracks by telephone calls, e.g. from manual control centers in the Albuquerque, Minot, and Oklahoma City sectors, could be entered via consoles of the fourth-floor manual inputs room adjacent to the communication recording monitoring and VHF room. In 1966, SAGE communications were integrated into the Autovon network. SAGE Sector Warning Networks (CF). NORAD Division Warning Networks provided the radar netting communications for each DC and eventually also allowed transfer of command guidance to autopilots of TDDL-equipped interceptors for vectoring too. SAGE Direction Centers and Combat Centers were also nodes of NORAD's Alert Network No. 1, and SAC Emergency War Order traffic included positive control/Noah's Ark instructions through northern NORAD radio sites to confirm or recall SAC bombers if SAC decided to launch the Alert 4. A SAGE system ergonomic test at Luke AFB in 1964 showed conclusively that the wrong timing of human and technical operations was leading to frequent truncation of the flight path tracking system. Harold Sackman. 9. SAGE software development was grossly underestimated, 360,000 lines in September 1955. The biggest mistake of the SAGE computer program was underestimating the jump from the 35,000 WWI instructions to the more than 100,000 instructions on the N/FSQ-8. NORAD conducted a SAGE/Missile Master Integration/ECM-ECM test in 1963, and although SAGE used AMI's input of air traffic information, the 1959 plan developed by the July 1958 USAF Air Defense Systems Integration Division for SAGE air traffic integration SATIN was cancelled by the DoD. Radar stations. SAGE radar stations, including 78 DW line sites in December 1961, provided radar tracks to DC and had frequency diversity FD radars. United States Navy picket ships also provided radar tracks, and seaward radar coverage was provided. By the late 1960s, EC-121 Warning Star aircraft based at OT's AFB-MA and McClellan AFB-CA provided radar tracks via automatic data linked to the SAGE system. Civil Aeronautics Administration radars were at some stations, e.g. stations of the Joint Use Site System, and the ARS-RMNS-1 air route surveillance radar rotation rate had to be modified for SAGE IFF/SIF modes Roman 3 and Roman 4 antenna gearbox modification for compatibility with F-21-1. Interceptors. ADC aircraft such as the F-94 Starfire, F-89 Scorpion, F-101B Voodoo, and F-4 Phantom were controlled by SAGE GCI. The F-104 Starfighter was too small to be equipped with SAGE data link equipment and used voice-commanded GCI 229, but the F-106 Delta Dart was equipped for the automated data link ADL. The ADL was designed to allow interceptors that reached targets to transmit real-time tactical friendly and enemy movements and to determine whether sector defense reinforcement was necessary. Familiarization flights allowed SAGE weapons directors to fly on two-seat interceptors to observe GCI operations. Surface-to-air missile installations for CIM-10 Bomarc interceptors were displayed on SAGE consoles. Improvements, replacement and disposition. For airborne command posts, as early as 1962, the USAF declared full operational capability of the first 7 Joint Surveillance System ROCs on December 23, 1980, with Hughes and /FYQ-93 systems, and many of the SAGE radar stations became Joint Surveillance System JSS sites, e.g. San Pedro Hills-39 became FAA ground equipment in 1996, and /FSQ-7 components were moved to Moffett Federal Airfield for storage and later moved to the Computer History Museum in Mountain View, California. The last and /FSQ-7 centrals were demolished at McCord AFB August 1983 and Luke AFB February 1984. Decommissioned and /FSQ-7 equipment was also used as science fiction cinema and TV series props, e.g. Voyage to the Bottom of the Sea, amongst others. Historiography. SAGE histories include a 1983 special issue of the Annals of the History of Computing, and various personal histories were published, e.g. Valley in 1985 and Jacobs in 1986. In 1998, the SAGE system was identified as one of 4 monumental projects, and a SAGE lecture presented the vintage film in your defense, followed by anecdotal information from Les Ernest, Jim Wund, and Paul Edwards. In 2013, a copy of a 1950s cover girl image programmed for SAGE display was identified as the earliest known figurative computer art. Company histories identifying employees' roles in SAGE include the 1981 System Builders, the story of SDC, and the 1998 Architects of Information Advantage, the MITRE Corporation since 1958.